So before we explore this cat and mouse game, let me actually motivate the reasoning for this problem, at least one reasoning. So if you have two random walks exploring a large graph, you're kind of interested, when will they meet next? So this problem is, maybe these two random walks are walking in this graph, they're exploring, and when they meet, they have to perform some action. And we want to understand how often they will meet. So that's kind of the motivation for this problem. But of course, um, being good theoreticians, instead of posing the problem in that manner, we'll try to pose it in a little bit more fun way. So in this, we treat this as sort of a game between a cat and a mouse. They start at their own independent locations, and they do their own independent random walks. They start at the same time. And then we ask, then this is an arbitrary graph that they're both exploring. And when the cat and the mouse meet, as that is, when they both, while they're doing the random walks, if they both come to the same vertex, then the cat will eat the mouse. So the question we are interested in, we're going to pose it in the following way. We want to show that O of m squared n is an upper bound on the expected time before the cat gets his meal. Basically, the time the cat will reach a vertex where the mouse will also be present. Now, to understand this problem and find a way to get a handle on this, what we should do is consider a new graph, and we call that graph G star. Okay. And in this graph, there are more vertices. There are actually n squared vertices. Basically, every pair of vertices in the original graph forms the set of vertices. In fact, every pair where each of the pair is drawn with replacement. So you even have pairs of the form u where it doesn't we don't need both the vertices to be distinct. Okay, so that means that we really have n squared vertices in this new graph G star. But how do we place the edges in this new graph? So you consider two vertices u and uv and u prime v prime in this new graph G star. Now there will be an edge between these two vertices if and only if u prime was an edge in E, and also v comma v prime was an edge in E. So in other words, the intuition is the following. The first, if you look at any such vertex, the first one gives you the current location of the cat in the original graph G, and V kind of gives you the current location of the mouse in the original graph G. So so that's the intuition, and then you can immediately notice that a random walk in G star that reaches any vertex of the form u corresponds to the cat getting its meal. Why? Because, well, both the cat and the mouse are in the same vertex. So then the cat will eat the mouse. Now, we just saw a little while ago, or rather we reminded ourselves a little while ago, that the expected time to cover the entire graph and therefore also reach a vertex of the form UU is going to be at most m square n square, because this graph G star has at most m square edges, and we saw that it has n square nodes. Okay, but we need to show something a little bit tighter. If you recall, what we need to show is that the cover time is m squared n. So we need to shave off a factor of n. So how do we do that is the question. So let's think about why that might be the case. I leave you with one intuition. So now let's look at this graph G star. Okay. Now wherever be your starting point, u comma v, you first argue that there is a path of length at most n that will then lead you to a vertex of the form s comma s. Okay, and now we know what is the time, the expected time to go from here to here when you're doing a random walk, and similarly you know the expected time to go from here to here, and so on. You can add them all up. This whole thing will be of length n. Each one of them, each one of these components we need to argue is going to be at most O of um, m squared, and therefore we should be able to get the final result. So that's the sort of the technique that we will need to follow in order to be able to prove this claim.